All right. So this is 2.3, number 2, and it's a subgroup proof. So remember subgroups. Let's get the definition here. So a subset H of a group G is a subgroup of G if and only if these three things are met. H is closed under whatever the binary operation is. So we could write this like this. G star is closed under star, right, the binary operation of G. 2, the identity E that's in G is also in H. And for all A in H, A inverse is also in H. Okay, so every element has its inverse as well. Okay, so for our proof, we have to assume H is a subgroup of G and K is a subgroup of G. Okay, so that means that H has closure, the identity, and inverse elements, as does K. Okay. All right, so we're trying to show that the intersection of H and K also forms a subgroup using star. Okay, so let's write that out. Want to show H intersect K is also a subgroup of G. Okay, so first, check if H intersect K is closed. Okay, to check if something's closed, we take two elements from it, A and B, and we want to show that A star B is also in H. That's to show H is closed, right? For any A and B in H. Here, let me write it like this. Sorry. For any A comma B in H, the product, A star B or A times B, that's also how it's often written, AB is in H. Okay, that's when you start getting extra lazy and leaving off the star, because people call it multiplication, so AB would be the product, which is the same as A star B. Sorry for that terrible confusion, but that's how it works. Okay, so check if it's closed. All right, so we're gonna pick. Let's let A and B be in H intersect K. And we want to show, the goal is down here to get that therefore A times B, or A star B, or AB, is also in H intersect K. Okay, so if A and B are in H intersect K, then A and B have to be in H, and A and B have to be in K, because that's the definition of intersection. Okay, well, if A and B are in H, I know that A times B has to be in H, because H is closed, because it's a subgroup. And similarly, K is closed, because it's a subgroup. Right? H and K are closed because they're subgroups. So we're guaranteed that if you pick a couple elements and perform the binary operation with them, you get another element in a group. Well, that means A star B is in H and A star B is in K, so I can actually jump straight to this step. Whoops. Let me move that up. Right there. And that is because definition of intersection. Therefore, H intersect K is closed. Boom. Done with that part right there. Okay. Next one we need is show that the identity from G is also in H. Show that the identity from G is also in, and in this case it's H intersect K. Okay. Well, we know since H and K are subgroups of G, the identity from G must be in H, and also since K is a subgroup, the identity from G must be in K. Well, since E's in H and E's in K, E has to be in H intersect K. And the same thing, definition of intersection. Well, therefore the identity E of G is in H intersect K. So we're done with that part. Okay, let's look at 3. So check if you know that A is in your subgroup, or what you're trying to prove is a subgroup, then its inverse has to be in the subgroup too. Okay, so we're going to start with A. Let A be in H intersect K. Then the goal is to show that A inverse is. Okay? Well, since A is in H intersect K, A has to be in H, and A has to be in K. Right? Definition of intersection. Well, if A is in H, and H is a subgroup, then A inverse has to be in H. Because H is a subgroup, and we know that for every A in H, A inverse has to be in H. Same deal with K. Right? Because H and K are subgroups. And for any A in H or A in K, the inverse has to be in there. I'll do it like this. There we go. Well, that means that A inverse has to be in the intersection. Definition of intersection once again. Okay, so we satisfied rule 1, rule 2, rule 3, or axiom 1, 2, 3, or whatever you want to call them. Stipulation. So by parts 1, 2, and 3, we know H intersect K is a subgroup of G. Okay.